Hello, my name is Jakub Jatek, and this is Joint Work with Lorenzo Beretta. So in this talk, we will be considering the following problem. Suppose that we have a set of numbers, and we want to estimate their sum. And we are assuming that we can sample these numbers with probabilities proportional to their values. So formally speaking, we have some universe U of size n, and each item A from this universe has its weight W of A. And we can sample proportionally, which means that any item from this universe is sampled with probability equaling to its weight divided by the total weight of all the items. And for two sampled elements, we are assuming that we can determine whether they are equal or not. So this is the setting, and now our goal is to estimate W, which is defined as sum of all the weights of all the items. Or in other words, we want to get some W hat, which is a 1 plus epsilon relative approximation of W. So we call this the proportional setting. We can also add the assumption that we can also sample uniformly from the universe, and that is called the hybrid setting. So now just to show you of where this occurs in the real world. So suppose that we have some graph, and suppose that we can sample edges uniformly from this graph. So that is our assumption. Now set U from the previous slide, the universe, to be the set of all vertices, and the weights will be the degrees of the vertices. And now we can implement proportional sampling as follows. So we pick an edge uniformly at random, and then we pick one of its endpoints again uniformly at random. And it can be shown pretty easily that this actually implements the proportional setting. Moreover, it holds that W, the sum of all the weights, which is the sum of all the degrees, is twice the number of edges in the graph, which means that any algorithm in the proportional setting for the sum estimation problem can be used to estimate the number of edges in a graph under the assumption that we can sample uniformly from the set of all edges. We can also add, again, the assumption that we can sample random vertices, and that will implement the hybrid setting. So now I will compare our results to the previous work. So in this paper, the authors have shown upper and lower bounds, and these bounds match in terms of the dependency on n up to polylogarithmic factors. We improve both their upper and lower bounds, and we get something that is matching up to constant factors in both in terms of n and epsilon, with some exceptions where we almost get it match up to constant factors, such as here, where we get the additional logarithm, or here, where we get the additional epsilon squared term. We also extend their results to the setting when the universe size n is not known to the algorithm. So nothing was previously known in these settings. So we also consider that, and we get optimal or near optimal algorithms. We also give a new algorithm for estimating the number of edges in a graph. Now, of course, any of the algorithms from the table also imply an algorithm for estimating the number of edges in a graph, as I have argued on the last slide. But we also give sort of a separate algorithm for this problem, and it runs in this time complexity for d being the average degree, and it is under the assumption that constant fraction of vertices is non-isolated. So we say a vertex is isolated if it has degree 0. The algorithm actually works also without this assumption, but then the complexity is slightly more complicated. It is in the paper. And it is in the setting where we can sample both edges and vertices uniformly. So now comparing to the previous work, which was under the assumption that we can sample uniform vertices, in that work, we get one of these complexities depending on the exact setting that we assume. But now suppose that we set epsilon to be constant, and we set also the average degree to be constant. So the number of edges is roughly the same as the number of vertices. And then if you look at these complexities, then all of them are equal to n they are equal to square root of n times polylog of n. Whereas our algorithm in this range, or under this assumption on epsilon and m, is much faster. It has constant complexity actually. So in the rest of this talk, I will be focusing on this result. I will be showing both the algorithm and the lower bound. Actually, this algorithm is very simple. So it is actually so simple that I will be able to show it in almost the full detail. And then I will briefly sketch a simplified version of the proof of our lower bound. So now for the algorithm, suppose that we pick A proportionally, and now we let X to be the inverse of the weight of A. Now we can calculate the expectation and the variance of X. So if we look now at the expectation, in some sense, it's very nice. So the expectation is not equal to W, which is the value that we want to estimate, but it is some nice function of W. So specifically, if we have a good estimate of the expectation of X, then we can just divide it by n and take the inverse value, and that will give us a good estimate of W. However, if you look at the variance, we can upper bound that like this, and this upper bound is actually pretty tight, which is equal to this. And here we have a sum of the inverses of the weights. And that's a problem because just by making one of the weights very small, that will give us that the variance can be arbitrarily large. So we are not able to get a good estimate of the expectation. So we need to do something different. So now suppose that we could somehow square this fraction. Now that would be very nice because then we would get this, and here the this weight and these weights, they would cancel out. And these are exactly the weights here, which are causing us all the trouble. So that would be good because then this would cancel out and we would get this very nice upper bound on the variance. So now we need to somehow modify the algorithm to achieve this. So we will use the following algorithm. We will sample 2 items instead of 1, A1 and A2. And if they are not equal, then we set X to be equal to 0. And otherwise, we let X to be equal to the inverse of their weight. Now note that for any A from the universe, it holds that A1 and A2 are both equal to A with this probability, and this is just by independence. Now we can again look at the expectation and variance. So now the variance is exactly what we wanted, as I have shown on the last slide. And the expectation again is very nice in that it is 1 over W. So if we have a good estimate of the expectation, then we may just take the inverse of that estimate, and we will have a good estimate of W. So what we can do is that we could take average over this many independent runs, and that would give us by a standard formula for variance, it will give us that the standard deviation is equal to this, which means that by Chebyshev with any constant probability, it holds that we have a 1 plus order of epsilon relative approximation of the expectation of X. Now, not an estimate of W yet, but such estimate of the expectation of X. But as I said, we can just take the inverse value, and that will give us a 1 plus order of epsilon approximation of W. And just by changing these constants, increasing the constant here, this will lead to 1 plus epsilon approximation of W. So this is an algorithm which has bounded complexity, so that's good. But the complexity is much higher than what we wanted. We wanted square root n divided by epsilon. So actually we wanted to have complexity which is the square root of this complexity. So to get this, we use the following trick. So note that our estimator actually needs 2 items. That means that if we make a sample of size k, then we can consider one such estimator for each pair of sampled items. And that will give us order of k squared estimators. And now pleasant surprise is that these estimators are actually uncorrelated. So, and because we are trying to upper bound the variance, being uncorrelated is as good for us as being independent. And on the last slide, I said that we need this many independent runs. But now using this trick, it is actually sufficient that we have this many pairs in the sample, which means that the sample size, it has to be this, and that's sufficient. So now we got an algorithm which has the desired sample complexity. Now it turns out that actually we can take this algorithm and we can simplify it into a very simple formula. So I will show that on the next slide. So let us have some sample S of this size, and we let S prime to be the set of the sampled items. So S is the sample, that's a multiset, and S prime is it's a set without the multiplicities. Now for S in S prime, we define C of S to be the multiplicity of S in the capital S, in the sample. And now what I've shown on the last two slides, the algorithm, it can be simplified to this formula. Okay, so that's it for the algorithm, and I will now focus on the lower bound. So as I said, I will be only showing simplified version of the proof. Specifically, we will assume that epsilon is at least this big, and that allows us to use simpler construction in the lower bound, making the whole proof much easier. So now I will construct the hard instance that we use in our lower bound. So with probability equal to 1/2, we set all the weights of all the n items in the universe to be equal to 1. And otherwise, also with probability 1/2, we set almost all to be equal to 1, but for epsilon fraction of them, we will set it to be 0. Now notice that between these two cases, the sum of the weights, it differs by a factor of 1 minus epsilon. So if we can show that it is hard to distinguish between these two cases, then it's also hard to estimate the sum of the weights. And notice that in the proportional setting, we are sampling uniformly in this case, and we are sampling uniformly from the first this many items in the case 2, and we are never sampling from these items because those have value 0, so those have probability 0 of being sampled. So now the way that we prove the lower bound, the way that we prove that it is hard to distinguish between these two cases, is that we will prove this claim. And actually, I will now try to just very briefly sketch an intuition of why this is sufficient. So we have this assumption that S is smaller than the desired lower bound. And I'm claiming that we prove that with probability at least 0.99, in that case, this holds. So what this is saying is that the probabilities of the two cases, conditioning on S, are roughly the same. Now, intuitively speaking, if you want to make a guess whether we are in case 1 or case 2, then what we want to do is that we want to look at the posterior distribution, conditioning on S, the sample, and we want to guess that we are in the case which is more likely, right? If you want to maximize the probability that you are right, then you just want to guess that you are in the case that is more likely. Now, if this holds, then the probabilities are both roughly 1/2, and that means that even if you choose the case which has greater probability, its probability will be still just slightly larger than 1/2, and that means that in that case, on this event, we cannot distinguish between those two these two events with probability much greater than just a coin flip, just 50-50. So actually, this would allow us, it will allow for the possibility that we can distinguish between those two cases with maybe like 52% or something like that. But actually, for any fixed probability strictly greater than 1/2, it is equivalent distinguishing between these two cases by probability amplification. So it's not important what probability we actually try to prove. Okay, so as I have argued, if we can, as I have given the intuition for, if we can prove this claim, then the lower bound will follow. So in the rest of this talk, I will try to sketch how to prove this, or how we do it in the paper. So the way that we start is that we compute this fraction. So we express this fraction as a function of S, as a function of the sample. Well, actually, it turns out that this function is very nice. Specifically, this fraction, it only depends on the number of distinct sampled items in S. From now on, we will be calling this quantity L. And then what we do is that we prove that it doesn't matter in which case we are. In either case, this L will be lying in some interval from A to B with probability at least 0.99. And then a very important part of the proof that we do in the paper is that we give some bounds on A and B. And basically what we show is that this interval is very small. And the way we do this is that first we prove that the expectation of L is roughly the same in both of the two cases. And then we show that L is concentrated around its expectation. And this together gives us that there is some pretty small interval such that we lie in this interval with probability 0.99. And now we take this, and basically what we do is that we plug in this interval into the formula that we have gotten here. And specifically what we show is that for any L in this interval, these inequalities that we wanted to prove, they hold. Right, and this proves this claim because now with probability 0.99, L is in this interval, and if that is the case, then these inequalities hold. So we have proven the claim. Now, unfortunately, from the way I have explained it, it is not obvious how we use this assumption, or even why this is the correct function. So actually, the way we use it is that in these computations where we give the bounds on A and B, we use this assumption, and we also use the assumption on epsilon being not too small, and we use them to prove that the interval from A to B is small, and that's what allows us to give good bounds on the ratio between the probabilities. Okay, so this concludes the sketch of the proof of the lower bound. So in summary, in our paper, we have given matching and near matching bounds for the sum estimation problem in both the proportional and hybrid settings. We do this while improving both upper and lower bounds upon the previous work, and we also extend the results to the setting where the universe size n is not known to the algorithm. And we also give an algorithm which is specific to edge counting. So it's an algorithm which doesn't work by solving this general sum estimation problem, but we go directly and solve edge counting. And in this talk, you have seen an algorithm for the sum estimation problem in the proportional setting. And you have also seen a sketch of a lower bound for this setting. Okay, so that's it for me, and have a nice day.